So the purpose of this video is to help understand how to calculate the electric field inside the outer conductor of a coaxial cable using Gauss's law. So the picture that we've already drawn on here shows the inner conductor being solid, the outer conductor being solid. I'm going to focus my attention on the outer conductor because I think that's the hardest part of the problem. Bear in mind that this is not a sphere, this is instead a cylinder, and so we're looking at something that is going to be using the equations of a cylinder rather than the equations of a sphere. So what we know is that we can apply Gauss's law to say that the electric field multiplied by the area is equal to the enclosed charge divided by epsilon 0. So we're understanding that. The area is going to be the area of the sides, of the curved sides of a cylinder. And so the electric field multiplied by the circumference of the circle, 2 pi r, and then where r, by the way, is going to be the radius of our Gaussian surface. And so the r is going to be arbitrary, but we know that it's going to lie between B and C. And so the r is shown here. I'll go ahead and use a capital R. I'll be consistent and use a capital R over here as well. And of course that's multiplied by the length of the cable L as well. So 2 pi r L is going to be it's going to be the area of the curved sides of the cylinder that forms the Gaussian surface, and that's equal to Q enclosed divided by epsilon 0. So the 2, the pi, the r, the L, those are all going to be known to us. The electric field is what we're trying to solve for, and so we can put that over onto the right hand side. So we have Q enclosed divided by 2 pi epsilon naught r times L. And so then the problem reduces down to how much charge is enclosed within the Gaussian surface that has its boundary inside the outer conductor. Well, first of all, we know that the entire inner conductor will be included. So when I'm calculating the Q enclosed, right off the bat I know that it's going to include all of the positive charge on the inner conductor. So this is plus Q, but then there's also going to be a portion of the charge from the outer conductor. So we're going to say minus Q. Now if it had the entire outer conductor, that would be it, and then that would add up to 0. But it doesn't have the entire outer conductor, it only has a portion of the outer conductor. And so that portion is going to be related to the relationship between R and B and C. So what we probably ought to do is take this and make this be the volume density multiplied by the volume, the amount of volume that we have on the outer conductor. And so those two things we can calculate separately. Now the rho sub v is going to be we can calculate that as the total charge divided by the total volume. Now the total volume of this outer conductor, we could calculate that. So the volume is going to be equal to the volume of a cylinder that was around the entire outer perimeter here, but then we have to subtract off the volume of a cylinder that had the inner volume. And so the total volume of the entire cylinder, let me say the total volume of the entire cylinder, or you could think of that as like a tube. That's going to be pi c squared times L minus pi b squared times L. So that's the volume of a large cylinder that has a radius of c minus the volume of the smaller cylinder that has the radius of b. So that would be the volume of the cylinder, and the charge density, rho sub v, is just going to be the total Q. So it's going to be Q divided by pi c squared L minus pi b squared L. And so that's the charge density. Now the volume of the Gaussian surface that's contained within that is going to be the volume is equal to pi r squared L minus pi b squared L. And so what we want to do is we want to multiply the rho sub v that we calculated here by the volume that we calculated here. And when we do that, we're going to find out how much of the negative charge is included in the enclosed charge. So when we multiply those together, we end up with Q times pi r squared L minus pi b squared L divided by pi c squared L minus pi b squared L. And lots of things are going to cancel. The pi's are all going to cancel. The L's are all going to cancel. And we're going to be left with that it's Q times, and I probably ought to switch back to lowercase letters here so that it matches the posted version. It's r squared minus b squared over c squared minus b squared. Remember that that is the quantity that goes up into this part of the equation right here. So the total charge enclosed, is Q times 1 minus r squared minus b squared over c squared minus b squared. And we can then calculate the linear charge density, rho sub L. So now if we think of this not as a three-dimensional object but simply as a one-dimensional object, rho sub L is going to be equal to Q divided by L. And so we can replace a little bit of the calculation that is going on up here. I'm not sure if I can squeeze this in now, but I'm going to end up with Q times 1 minus r squared minus b squared over c squared minus b squared. All of that divided by 2 pi epsilon naught r L. And notice that this Q and this L taken together form rho sub L. And I seem to have run out of space a little bit here, but this is going to end up being rho sub L times 1 minus r squared minus b squared over c squared minus b squared. All of that divided by 2 pi epsilon naught r. And that is the answer that was posted as the solution on the board. So sorry for the messiness. Sorry that it couldn't sort of get this all into one slide without squeezing it together, but I hope that that's helpful for you.